I'm Alex Chakarov, and today I will be talking about investigating student understanding of data displays using programmable sensor technology. This is work completed in collaboration with my co-authors from the University of Colorado Boulder and Utah State University. The problem this work addresses is the fact that all students need exposure and experience with computational thinking. This is a hard problem because many current opportunities are elective courses and after-school activities that require students to opt in. Our solution is to broaden participation in computational thinking activities through sensor-driven investigations in mainstream middle school science classes. We target mainstream science classes to ensure that all students receive exposure. We hypothesize a three-part approach called school-wide labs in partnership with Denver Public Schools. There is a school sensing platform that consists of programmable sensors that allow students to collect real data for scientific investigations, a set of productive integration tools such as model curricula and activities for both teachers and students to use, the CT integration cycle, which is a professional development model to support science teachers to implement the CT integrated middle school science lessons. We currently use the microbit, a small microcontroller designed for use in education that can be programmed in block or text-based languages. We worked with SparkFun, a small electronics company near CU Boulder, to enhance the capabilities of the microbit by adding the Gator bit, which exposes more pins on the microbit for easy prototyping with alligator clippable sensors, such as a sound sensor or a soil moisture sensor. The Gator bit also functions as a simple data display with 5 NeoPixel LEDs and a piezo speaker. The sensors have blocks in MakeCode that allow students to program the microbit to collect data. To develop the curriculum, we draw on an instructional design technique from science education that has been effective at implementing the next generation science standards, which aims to make science class look more similar to the work of actual scientists. Storylines are created before lessons to serve as unit guides, centered around a scientific phenomena that generates an overarching question for students to answer. After the introduction of the phenomena, students create a driving questions board. Similar questions are categorized into sub-questions that will help answer the unit driving question. We extend this approach to support computational thinking through the use of programmable sensor technology. Storylines are created to ensure a coherent, relevant lesson set that supports incremental knowledge building. We designed the CT integration cycle to support teachers to implement the CT integrated science units. The CT integration cycle draws on collaborative design between researchers and teachers. Workshops that contain a significant co-design component are highlighted in yellow with horizontal stripes. The model also draws on the problem-solving cycle, a professional development model for math education. The workshops outlined in green checkerboard draw on the problem-solving cycle where teachers work together to plan and adapt parts of the unit for implementation. Select lessons are videotaped, mainly focusing on the unit launch and the sensor technology that guide the reflection workshops. We utilize a design-based implementation research methodology to create and study the different pieces of school-wide labs. This is a strategy that organizes a collaboration between researchers and practitioners focusing on solving a problem of practice. Our problem of practice came out of conversations with Denver Public Schools, our practitioner partners, that highlighted their need to integrate computational thinking in equity-driven ways. Before diving deeper into the analysis of the CT integrated units, this is a short video highlighting the project as a whole.
This project is really important for the state of Colorado and the nation as a whole because we are looking at how to make learning computational thinking inclusive for all K through 12 students. Currently, most students who learn computer science and computational thinking in middle school and high school do it through electives. So these are optional courses that not all students take. And so we want to make sure that all students have access to this body of knowledge. So that's why with this project we're focused on embedding computational thinking into mainstream science courses that are required and that all students must take.
Most of our initial goals were surrounded by the adoption of next generation science standards in our state, and how can we prepare teachers to transition to those. That was one of the big pieces.
A lot of time brainstorming different phenomena that meet a set of performance expectations for the next generation science standards. And then there's an additional aspect that we're trying to focus on sort of this place as a construct in the classroom, because one of the things that we hypothesize is that when kids actually get to sort of do investigations that are grounded in their school or in their local community, that hopefully we're going to increase interest in underrepresented groups because it's a little more real.
First of all, it's a partnership, bringing together sort of the industry, academia, and public schools with the ultimate goal of increasing kids' engagement at middle school level in science, computational thinking, which is really a form of computer science education, by bringing in all these kind of consumer-grade electronics that are affordable, which is very important for a school district, are programmable in simple ways, and are mobile. And integrating that within the science curriculum to make science more interesting and to help kids begin to explore ideas in computer science, and thinking about that it can actually have an artistic dimension, that it can really help you ask deep questions about the world around you and help you understand the world around you.
It's a great idea, using these sensors where students can collect their own data and they can own that data instead of just looking at something through a module or a simulation. They can go out, collect the data, own the data, and then design their own tools through computational thinking.
There's several takeaways. One is that kids in middle school can engage in science activities where they ask deep questions about the world around them, use modern scientific equipment and technologies to address them, and come to care about the answers. And that's an important and significant shift for how lots of science instruction has happened and continues to happen.
The rest of this talk discusses the third design cycle of the School-Wide Labs project. We worked with 10 teacher partners during the third design cycle. A lesson learned from the first two design cycles is the teacher's desire to spend time having their students explore the technology to see how it can be part of their scientific toolkit. To address this issue, we co-designed a sensor immersion unit that aims for students to see the programmable sensor technology as an instrumental tool to support their scientific inquiry and to gain adequate knowledge of the technology to use it independently. The driving question, how can sensors help us understand and communicate information about the world around us, anchors the unit. Students investigate two classroom data displays created using the same sensor technology available to them, a classroom environmental display and a display that monitors the moisture of a classroom plant. To understand how these displays work, students create and update hand-drawn models of the data displays throughout the week-long unit as they build their own miniature data displays. The goal is for students to frame other scientific problems as sensor problems and develop a robust model of how they work. We explored the following research question: to what extent did participating in the sensor immersion unit help students build understanding of the different aspects of the programmable sensor technology? To answer this research question, we analyzed 213 student models from 4 classroom teachers. The analysis of the models was complemented by teacher interviews and written reflections along with classroom observations. Examining student models for facets of student thinking has been useful in science curriculum as a way to build classroom discussion using the ideas the students present in their models. We worked with the teachers to develop an initial set of categories based on the ideas represented in the student models and then refine them into 4 categories. We examined only the final models since all 4 teachers had their students complete final models. The components of the display represent the different pieces that make up the display: the microbit, gatorbit, sensors, alligator clips, and lights. The flow of information in the display describes how data moves throughout the system between the microbit, sensors, and lights. The description of what the display shows highlights what information the display provides. The control of the display details how programming the microbit controls the entire system from data collection to data display. The modeling activity was challenging for the students, but we learned a lot about their understandings and struggles. This information will help as we revise the unit. Students were best at identifying the model's components, which makes sense because they are the parts that they are interacting with. Students struggled the most with the flow of information. The model on the left illustrates a common struggle where students were confused about where the sensor was located. Students would be confused after programming the microbit and not attaching the sensor as to why the reading was always 0. The model on the right represents a deep understanding with all components clearly labeled. Students struggled to illustrate the flow of information within the system. Some students described how data moved from the sensor to the microbit, but few students discussed how information was flowing from the microbit to the sensor. Students see the sensor as being in control, whereas the microbit actually has to ask the sensor for information. Students were most successful at describing the components. Some also exhibited understanding around data moving from the sensor going to the microbit, as well as the necessity of programming. Students struggled to differentiate between the microbit and sensors and how information flowed from the microbit to the sensors. Teachers shared these difficulties based on the language they used around the microbit and sensors, as well as the models they constructed during a workshop. The unit was not without its successes. Students did generate questions around the technology to drive the unit and successfully built mini data displays. Anecdotes from teachers describe the students seeing the sensors as an instrumental part of their scientific toolkit. We are currently working on a revision of the sensor immersion unit to enrich students' thinking around the programmable sensor technology. Instead of telling students this information, the goal is to revise the sensor immersion unit so that the students come to these understandings on their own through more in-depth exploration of the displays and discussion with both classmates and their teacher about how the entire display functions. This paper described a strategy to work with science teachers to collaboratively design science units that incorporate computational thinking using programmable sensor technology. Using hand-drawn models provided insight into students' thinking around the functionality of the programmable sensor technology and how information flows through the system.